Alright, so this is our first real video on Lie theory, and to start off I kind of just want to cover because Lie theory is mainly about Lie algebras and groups. We're mainly going to be looking at algebras actually, so I want to make sure we have a good foundation for what an algebra is, what a Lie algebra is, and then maybe get into start getting into what kind of properties it has. We'll see how that goes. But to start off, quick reminder, what is an algebra? There's two ways you can define it. There's one for rings, and there's one for fields. They're both very closely connected, though. As you can probably remember, from a field, on top of that you can construct a vector space, which is basically a set which is closed under its own kind of internal addition. And it also has a scalar multiplication, which is how it relates back to the field. And for rings, we have an analogous construction with modules. The only difference being that they're over a ring instead of a field. And then from either of those, we can construct an algebra. And obviously the difference between the two, based on a module, is going to be a bit more general. Based on a vector space is going to be a bit stronger. And so what additional structure are we going to be adding on to the vector space to turn it into an algebra? Well, what we're adding in is an internal multiplication. And so I'll write it as we're not going to use this X symbol because it's kind of messy, but just for the sake of writing it out. And I'm going to write the base field as I guess, I hope that doesn't keep popping up. Sorry, I'm going to have to look into that. We'll say over the vector space, it's going to be analogous over the field, obviously. It's going to be a binary operation. And the only constraint on it for just a regular algebra is that it has to be bilinear. It should be pretty clear what that means just from the name. But to review, an operation like this is linear basically if it commutes over those two operations that are pre-existing that we mentioned, addition and scalar multiplication. So basically, for x and y, x, y, and z in our vector space V, and for a scalar, I'll say A in the field that this vector space is based on, we have that multiplication should distribute over addition, and it should also distribute over scalar multiplication. Now, this is going to look a little funny. Keep in mind what's happening here. This is scalar multiplication. So this is f times v, and then that's returning a vector that we're then multiplying with our new operation. And what this is saying is that is compatible with doing the vector multiplication first. And this is going to be, these two conditions are going to be holding in both arguments. And the construction looks exactly the same for rings and modules. It's just, yeah. And I want to emphasize here, that is the only constraint we have for an algebra in and of itself. It doesn't have to have an identity, it doesn't have to have inverses, it doesn't have to be commutative, it doesn't even have to be associative. Even with most of the constructions you see, I find in abstract algebra, like groups and rings out, you always have at least associativity. We don't even have that here. Just by linearity, that is an algebra. Now, what makes it a Lie algebra? For a Lie algebra, we're going to have two more constraints. My writing is very messy here. I'm gonna have to figure out something here. I'm sorry, this is first videos. It's gonna be a bit of a rough start, but that's how it goes sometimes. Now, first off, for our Lie algebra product, we often talk about it in relation to the standard product. So we write the product as this. We call this the Lie bracket. And the Lie bracket has to have three conditions. First off, it needs to be bilinear, as we said. Now, our second condition, there are two different ways you can talk about it. They're not quite the same. The first, okay, there's two similar approaches. The first is called alternativity. You may have seen this if you've looked at like a wedge product before. What alternativity says is just that the bracket of any element with itself, so product, is always 0. For all x in, we'll call it G, kind of confusing. It kind of looks like a group, but that's just the standard notation for it. And the second definition you often see, I'm probably going to subconsciously refer to it as anti-symmetry, but the more official name for it is anti-commutativity. And what anti-commutativity says is if you swap the arguments, it gives you the negative. Sorry, I'm gonna have to change my grip a little bit here on my pen. And at first these two things may look a little different, may look kind of unrelated. But we have first off that alternativity implies anti-commutativity. And the way we get that is just by looking at the bracket of x plus y with x plus y. Okay, yeah, I'm gonna have to figure out something there. And keep in mind, by linearity, we can essentially FOIL this. And so what we get is bracket of x with itself and x with y and y with x and y with y. But since we're assuming alternativity, we know that this one is 0 and we know that this one is 0. And so this gives us that this whole expression on the right reduces down to x comma y and y comma x. But this is just, this expression on the left is two elements, is the same element bracketed with itself. And so we know this has to equal 0. And what we get is essentially a rewriting of anti-commutativity. Now, does it work the other way? The answer is almost. The obvious thing to do here is to look at the bracket of x with itself, and then by anti-commutativity, that gives us this. Now, this looks like it gives you that x bracket x equals 0, but it doesn't work in characteristic 2. Just keep in mind that the everything is its own inverse in characteristic 2. And so this equation we have here isn't quite enough to give us alternativity. We're not going to be working a lot, to my knowledge, in characteristic 2. And so they're going to practically be the same thing. And I'm going to commonly refer to anti-commutativity, or probably calling it anti-symmetry. But just keep in mind that technically we are usually going to be defining this with alternativity. And as I mentioned before, there is one more constraint that we're going to put on this Lie bracket, and that is the Jacobi identity. Now, we're going to have a good justification for this later on, but we need a lot of definitions that we don't quite have yet. So at first this is going to look kind of arbitrary and nonsense, and for right now you're just going to have to play along with me. So what we do is we take the bracket of 3 elements. Keep in mind that this bracket is not associative in general, so this very well could be not associative. And we're just kind of cycling through them in the 3 positions. And this whole bracket has to add up to 0. And keep in mind that with alternativity, with anti-symmetry, and that you can switch around how it's being ordered. Like right now we're taking the bracket of x and this value, which is going to be the bracket of y and z. See, and then we can do a similar, we can use our existing properties created the other way, but this way with it on the right, it looks to me a little awkward, but it is actually the nicer way for reasons that we will get into later on. But for now, like I said, this is all going to seem a little mysterious at first, but there is a good reason for this. We might even see it today. I don't know how long it's going to take us to get through all this, but yeah. So the next construction we need to build, of course, are morphisms. Okay, I should say too, with algebras, you have all the typical constructions. You have products and all that. I guess that's maybe more suited to when we talk about ideals and that. So next up is morphisms. It should be pretty clear how this works, but if you have a function, we're going to write it phi between 2 Lie algebras from L to say L prime. This is a morphism if it splits over the bracket. So essentially that phi of the bracket of x and y is equal to the bracket of phi of x and the bracket of phi of y. Let's try to write that maybe a little nicer. And of course, all the typical stuff that goes along with that. If we want it to be an isomorphism, it needs to be, the function as a linear function needs to be isomorphic. Like this function here is going to be fundamentally a vector space morphism that also satisfies these conditions. And for isomorphism and all that, it just means that this underlying function as a vector space morphism needs to be an isomorphism. And once again, keep in mind all the time we'll be switching between this and modules. I'm only usually going to talk about one case, and hopefully it should be clear what the analogous situation in the other case will be. And one other thing I should mention, for now everything is going to be finite dimensional, and so a lot of times we're going to be talking about like the matrix representations of maps and all that. And that's because we're essentially doing this all over a finite dimensional vector space or module, as it may be. So let's go through a few examples before we talk about anything else, just so you can kind of like have a few reference points in mind as we cover this kind of thing. Now, the first off is if we have an algebra, I'll call it V, V be an algebra, then we can define our bracket of x and y to just be xy minus yx, where this multiplication is the multiplication from the underlying algebra. And this itself gives us kind of a few different cases to work with. Like, for example, one thing you can look at is note that if V is abelian, namely that x times y equals y times x always, then the bracket of any two elements is going to be 0. And this is a valid Lie algebra. It's not an exciting one in general, but you can take any vector space or module and just say the bracket over it is 0, and it does satisfy all the conditions, so that is something you can't count out. Another just kind of couple toy examples before we get into the heavy ones. I guess I should write this as like example 1. Example 2, let's look at R2, Euclidean space, two-dimensional Euclidean space. And we're going to write our basis with the E1 and E2 as you do. And then we can have our bracket of, we're going to write our bracket such that the bracket of E1 and E2 is E2. And note that this is enough to define the bracket everywhere. This is going to be our bracket, because you can think about it. If you take the bracket of E1 and E1, or E2 and E2, that is going to be 0 by definition. And the bracket of E2 and E1 is just going to be negative E2 by anti-symmetry. And then for any other vector in the space, you just have it by linearity and the fact that this is a basis. So this one equation is enough to basically, in this case, tell us what the bracket is going to do everywhere. And it's worth noting that in the two-dimensional standard case, this is essentially the only Lie bracket we can have other than the abelian commutative case of just it being 0. Because if you think about it, like I said, the bracket of E1 and E1 or E2 and E2 always has to be 0. And the bracket of E1 and E2 therefore that can be anything, and then E2, E1's can be its negative. And so then you can just you can show that you can do a change of coordinates to align to give you a basis such that you get this equation. I'm not going to go through the details here. It's not too important, that kind of thing, but it's worth noting. Another example which I like keeping in mind is, okay, it's just cool. Cool, big fan of that. 1 second. Okay, hopefully that fixes our issue here. So, the third example I want to look at today, let's get black because I gotta be edgy. Third example is let the bracket of x, I'll write it fancy, x and y be the cross product. Let's try to write a bit neater. It's very difficult with this, where this thing here is the cross product on R3. And you can show that this is itself a valid Lie bracket that satisfies all the conditions we've shown. Now, a couple more examples which I want to go into are the matrix Lie algebras, which first, to talk about that, we first need to talk about a Lie group. I briefly mentioned those before. None of the books cover them until much later on, but I feel like the matrix Lie algebras that we typically look at make a lot more sense with them in mind. I'm not going to go into any of the details here. I'm just going to give you a quick overview of the relation between Lie groups and Lie algebras. So what a Lie group is, informally, a Lie group, we're going to call it G, is both a standard group and it is also a differential manifold. The exact details of what a differential manifold is are not really important. It just essentially means we can do calculus on it. Essentially, what we specifically want is we want to make paths and kind of look at their derivatives. Now, every Lie group G has an associated Lie algebra, which I'm going to write as L, and the exact definition is going to be kind of weird at first. It's going to consist of elements of the form A prime at E, where A is a differentiable function from an interval negative epsilon to epsilon to G, and keep in mind this value E is the identity of our group G. Now, I guess maybe a better thing to call this is the tangent space of G at this E. So what is this essentially? What we have is G is some manifold, right? And now what we're looking at paths along G, and we're looking at essentially what speeds you can have at the identity. And the idea here is that this tangent space, along with some kind of abstract additional structure, we're not going to get into the details right now, is a Lie algebra. And so every Lie group is going to have an associated Lie algebra, and importantly, every Lie algebra is the Lie algebra of at least one Lie group, but it's not unique in the opposite order. And this is all, it seems kind of like abstract right now. It's nice to kind of like go through some of the details. Like I did exercises like this on this back in university, but I'm bringing this up now. I'm going to look at some, I don't know if this is the official name or not, hopefully it is, some matrix Lie algebras, and the name and how you think about them makes a lot more sense in the context of their Lie groups. So first off, we have the general linear group over some vector space. And what this is, these are matrices with determinant of your matrix being non-zero. If you think about this, the identity matrix has a determinant of 1, which essentially means you have some like wiggle room around the determinant, and so the related general Lie algebra, we write it with lowercases like this, and so these are just like any linear functions on our space V with no constraints. Like this can be 0. It can very much be like not surjective or injective. They're the same on finite dimension, right? And so this is also equivalent to the space of endomorphisms on V, which, a quick reminder, endomorphisms are morphisms from a space onto itself that are not necessarily isomorphic like an automorphism is. Now, the other major case, and this I think is the most important one, is the special linear. As a group, this is the group of matrices on V. I guess I should be specifying the dimension, right, of all this. And these are the matrices with a determinant equal to 1 exactly. So if you think about a kind of curve of matrices, which every matrix you get has determinant 1, that means the derivative of that function, the derivative of the determinant has to be 0, at least the first order. And it turns out that what that essentially is saying for our algebra, the special linear and algebra on V are matrices, n-dimensional matrices on V with trace of 0 exactly. That turns out to be the exact condition you need. I guess I should be talking about the bases of these algebras too. With the general linear group, this is just any n-dimensional matrix on V, so the basis of this thing is just elements of like this. What this is like a 1 in the I, jth component of the matrix, so it sends the ith basis element to the jth. It's just like, yeah, because this can be any arrangement of numbers in an n by n matrix. Another example you see a lot of, for example, our special linear case, we can look at the basis of, we're going to look at we're going to look at the basis of SL2 on R just to keep it easy. So keep in mind, elements in this algebra, they look like they can have any components, but we have this constraint that the trace, namely a plus d, has to equal 0. And so what we get is we get 3 elements. You can let a be anything, so we're going to say let a be 1, and that forces d1 to be 0, right? And then our off-diagonal elements, we can just put like a 0 in there. They have no constraints on them whatsoever. And for higher dimensional cases, it looks similar. Essentially, for this matrix on the left, you just have the same idea of like one element on the diagonal is 1 and the next is -1, and you continue along, and then just all of your off-diagonal elements are free. And that's the special linear case. Especially the two-dimensional case here is going to show up later on, so knowing this is pretty good, but otherwise, you know. And there's also other cases with like the symplectic algebra for the symplectic group and the orthogonal and all that. But let's keep moving on here. So now that we have a good understanding, one thing I forgot to mention. These matrix algebras, these special ones, a matrix algebra in general, the product is just going to be the matrix product. So the Lie bracket for these matrices is going to be the same one we saw before, where the bracket of two things, x and y, is just going to be x, y, minus yx, where these products are our matrix product. So up next, derivations. We're just going to keep on moving here. That was kind of a thing, but we're just going to go until the time is up. So a derivation is a linear map and call it lowercase d, and it is a unary map. That was a weird name for me, but unary map, and the condition that this holds is that when it acts on a bracket for x and y in L, it sort of splits across the bracket. So you get like dx comma y, and plus it's going to act on the other component. And this is our only constraint. And we get that the space of derivations on Lie algebra is itself a Lie algebra, not a Lie bracket. And we have our bracket working the same as usual. That's why I gave those two examples before of like the cross product and the right component, because a lot of the examples you see are of this form, and so it gets kind of easy to think that this is like the only way you can have a Lie algebra, and that's not true in general. Alright. Now, the adjoint next topic, which we're going to tie back to the previous one real quick, is the adjoint representation. For an element x in our Lie group, Lie algebra, for an element x in our Lie algebra L, we have a function that we're going to call ADX. It's going to be a function from L to itself. And the way it works, we write how it acts, I believe, using a kind of odd notation like this. This period is just showing that the adjoint representation is of x, and that function is acting on y, because without the period, it looks like the adjoint representation of x times y. And what this is defined to be is nothing more than our typical Lie bracket. So if you're familiar with the idea of currying from computer science, this is just the currying of the Lie bracket. And what's interesting is the adjoint representations of an element. I guess there's only one. I'm kind of trying to figure out what I'm saying as I'm saying it. Adjoint representations are derivations, is our first main insight here. Now, how do we show this? Well, first off, we write what we want to see. I guess that should be y and z. And keep in mind the definition of derivation is that this is going to split across the bracket. And keep in mind, we're starting with this because this is the only defining property of a derivation that we have. So this is saying that an adjoint representation is a derivation, and we want to get back to something that we have. I'm kind of writing this backwards, but whatever. And so what we're going to do is we're just going to actually substitute these in for the brackets themselves, as we saw before. And already you might be able to see where this is going. Because next up, our next step is to use anti-symmetry and bilinearity to put these all on the same side. I guess one thing, so the negative, and then keep in mind anti-symmetry, so we're going to flip this around. And anti-symmetry here, this is going to be minus x bracket z, right? But what is that? Well, so that's our bilinearity, and by anti-symmetry we can write that as this. And you may recognize this as the Jacobi identity. We just have our two other elements on the other side. But this is what the Jacobi identity is really saying, that the kind of brackets as a function, those are derivations. That's our third constraint. And so this is clearly a very important example of derivations. for a given derivation D, if there exists some component, some element x in our Lie algebra, such that D is equal to the adjoint representation of x, we see that D is inner. If not, D is of course then going to be outer. And so we have now, of course, we have that this kind of, think of this adjoint representation as a function going from L into the algebra of derivations of L. We build, and if we have a subalgebra, say, if we have a, if we have K in L being is a subalgebra, and it's going to be a Lie subalgebra, of course, with everything, basically you should probably figure what that means. It's a Lie algebra, and it is a subset of L. Then we have that the adjoint representation of a given element can be ambiguous, because like if we're writing, keep in mind this is all on a vector space, and these are all linear operations on vector spaces, and so they're all going to be matrices. And so even if the adjoint representation on a subalgebra acts similarly, it's going to have a different matrix. And so we're just going to keep track of that. And the way we do that is we just give ourselves a little subscript of where the adjoint representation is acting on. So like, as opposed to that, you don't always do that, but when it's necessary. These are going to have different matrix representations. I guess I shouldn't use the word representations here, because that is a thing that we're going to be going into. They're different matrices. And that is 45 minutes. We kind of futzed around before with like the program I'm using here. Let me take one quick check if there's anything more I should be talking about here, because like okay, next time we're gonna be starting our conversation at least with ideals. I don't know how far into that we're gonna go, but hopefully, I'm gonna be honest, it took me a while to get a recording setup that worked, given that OneNote crashes with OBS for some reason. So hopefully this recording turned out pretty good. I don't really have my next couple lecture things here planned out too far in ahead, but hopefully I should by tomorrow. Like, this was kind of a rough beta test here. Today I'm just doing the one recording, tomorrow too, and then we'll kind of see what my natural pace is, but I thought this was a good studying session. And yeah, see you next time. I guess this is more of a formal studying than anything. I shouldn't really have an outro, but you know, I can do whatever I want.